So, good morning to all of you. My name is Maurizio. I'm in charge to try to explain to you some details and give you some reading key. I mean, the the way on how to read and understand the um, GMA broadcast installation. Um, I can imagine that all of you knows perfectly which is the main planimetry of the GMA, but I think it's a good way to show you that. Okay, and Marco, please, can you give me the slides on slide number 4? Okay, as you can see on the slide, you have main functional areas which are divided in EQR1, CR1, pre-roll, and so on. Then we have EQR2, which is mainly due to the auditorium, polyvalent, and two external area completely independent, which are Bâtiment M and Toc Obivan. Why we are going to divide in this three-dimensional area? Because EQR1, CR1, pre-roll, and so on,
Sorry,
they
Maurizio.
have a technical prevalence over the entire system. So what does it mean? Um, if you look, please, Marco, can you change to the overall? If you look to the um plan, uh, not this one, but the overall, Marco, please. Okay, that's it. Uh, if you look at, this is the main area in which all the broadcast system are installed. The AQR1 is in this position, where is my hand now, and there are inside some equipment which are dedicated for the pre-roll, cour, minaret, esplanade, but also there are some equipment which are active into the polyvalent and the Toc Obivan. Um, the area that you can see here give you an overview of the system, but what does it not give you is the dimension. And dimension are fundamentals from broadcast point of view because we use wire, cable, and fiber. So just to give you a small view about the technical problem. When we talk about the dimension, if I want to connect, sorry, if we want to connect, why not? A building, let's call A, two building, let's call it B. I can use many different kind of a system, maybe wire, maybe fiber, maybe RF, but the main important is the distance. If the distance is too high, this is a limitation on which kind of a cable or media transmission I can use. In the system that we have built, we use for video coaxial cable, coax, and there are two type. One is VK50 which is a coax cable, a coax cable. Oh, sorry. A coax cable is a sort of cable doing like this one, in which um, in our case, the diameter of the cable for VK50 is sorry, is 4.5 millimeter. We use another kind of a cable instead of VK50, which is VK70. And the diameter of the VK70 is 6.9 millimeter. So this is bigger than this one. But the coaxial cable are limited inside the AQR room, AQR1 and AQR2, CR1 and CR2. This is because at 12G, which means 12 gigabit per second, the maximum distance that we can reach in VK50 is uh, 25 meter, no more than 25 meter. With the VK70, the maximum distance that we can reach is something between 33 to 40 meters. Of course, if you consider this distance, uh, we are just into the room. We cannot get outside in any way. This is the reason why we have made a choice to use this approach of the system. Within the room, let's say this is we have some racks, and within the racks we use from one rack to another we use VK50. Of course, if you look at, there are some monitors around and other device on the desk. Sorry. To reach this device, we use VK70. Uh, in this way, we can move at 12G the signal internally into the room. Of course, if you want to use a signal not 12G, maybe HD, of course, the distance will increase. Just to have a parameter, in VK50 at HD, you can reach more than 90 meter. With the VK70 in HD, we will reach more than 150 meter. But considering that we are using a lot of 12G, we have used a limit, and the limit is do not go more than 25 and 35 meter for each cable. um, that makes more limits in the system because from a general point of view, we decide to put a limit of 100 meter. Over this limit, we, instead of copper, I mean normal wire, we use fiber. that is valid for everything, including video, including audio, including Ethernet, and some other signals, control signals that we have to use. There are two exceptions to this limit, which are represented by the SMPTE cable and triax cable. Because for their nature, SMPTE cable and triax cable are um, built to reach long distance. Inherently, because SMPTE cable is hybrid one, hybrid, and use fiber internally to move the data, and copper for the power. Triax because it's a copper wire, but his characteristics is to move data and power uh, to reach distance more than 1,500 meter. We will get back on the triax cable later on because we use two different types of triax cable. And this is an old technology, but to have a compatibility with the old technology, if someone comes with the camera triax, we have installed also triax cable from some point to the OB van. So let's back now on the main slide. Marco, please, can you give me the main slide? As I told you, we have EQR1, CR1, prayer hall, mezzanine, cour, esplanade, garden, and minaret. All this area belongs to the EQR1 equipment. EQR2, CR2, the auditorium, the backstage of the auditorium, and its suite and archive belongs to the EQR2 electronics. But M and TOC Obivan are independent and can be they can exchange data, video, audio, and some other data with AQR2 and AQR1. So this is the AQR1 main functional areas where we have um, an area which is called AQR2, AQR1, sorry, which is equipment room 1, in which we have 6 racks full of equipment. And as you can imagine, this area will be cooled down appropriately because the temperature will increase due to the power dissipation from the device. This is the reason why there is this wall in the middle here and the door here. The other side is control room 1, where we have 3 desks. This one is video desk. This one is camera control desk. And closed in a separate area, we have the audio desk. Um, on the camera control, we have also the lights control, because we have a control of some lights on the prayer hall, mounted on the column of the prayer hall. So now we have some external slides which can help us to understand better what we are talking about. And the first one that we see is the schematics area plan, which is, Marco, can you switch please on the, yeah, okay. This is an overall about the entire system. The area included into the dotted lines are all the area belonging to the EQR1 CR1 and the EQR2 CR2. As you can see, we have the two external area which are, it's better if I, okay, doing this way, Bâtiment M with the GPS antenna, and here Doc Obivan. The other area, Minaret, Esplanade, Cour, and Prayer Hall, are connected to the EQR1, but also Obivan is connected to the EQR1, but in Doc Obivan we have just fiber which arrives and triacs from the floor box and wall box around. So what does it mean? The Toko Bivan is the interface between the entire GMA system and the EQR1 CR1, EQR2 CR2. That means a signal originated, sorry, a signal originated in pre-roll can be sent to the OBVAN, but also a signal generated into the EQR2 CR2 through the MediorNet, we will see later what does it mean, can be sent to the OBVAN. So the entire system has its interface with the external world in this position. What we can see here is very important, is this position in Bâtiment M, which there are some GPS antennas which receive a signal from the global positioning system and this signal is used as a sync reference for the entire GMA. We will see that later on in detail, but as you can see here, we have a fiber optic which give us the signal to the EQR1, and another fiber optics which is another core inside here, which give us the same signal which goes to the fiber GPS signal generator here in the EQR2. That means EQR1 and EQR2 receiving the same control from GPS are synchronized. Synchronized inside, but Equer 1 is synchronized, also referenced to the Equer 2 and vice versa. That means we can exchange audio and video between the two structures without any problem. So let's go on the Marco, please, can you exchange? No, stay there. Stay there. Sorry, stay there. Yeah. Um, it's it's understandable. Any question?
S'il y a des questions.
Hi Maurizio, I want
Hi.
just to understand what's the difference between the 4 GPS antenna.
Oh yeah.
Why we need 4?
Okay. This is the original drawings in which we had 4 antennas because the the Tor system. Tor is the manufacturer of the equipment, provides his equipment with 4 antenna. Along the time, they moved from sorry from 4 antenna to only 2 antenna. Right now we have 2 active antenna and 2 spare antenna installed. Later on we will see in details what we do with the antenna, but just to have an information, one antenna is dedicated to the Equer 1 and one antenna is dedicated to the Equer 2. The RF signal, GPS RF signal from antenna 1 goes to the Equer 1 and the RF signal from antenna 2 goes the Equer 2. There are 2 other antenna mounted on the roof of the Bâtiment M and already connected down in the technical room of the Bâtiment M. In case of trouble, it's just a question to switch the cable. GPS antenna are not simple antenna, but they contain also an amplifier. A simple antenna is difficult to destroy it because you can destroy it mechanically, but if contains electronics, it may be destroyed by electrostatic discharge or whatever. This is the reason why we move to have, instead of 2 antenna, to keep 4 antenna and use 2 antenna as a spare. Because if the GPS signal is lost, the synchronization between the 2 structure will be lost. And if the synchronization is lost, we have problem with the equipment. This is why there is a spare one and still 4 antenna, even if are active only 2. Is it clear?
Yes.
Hello, sorry.
Yes, Mauricio, it's clear.
Okay, perfect. So now we can move. Marco, please, still there. Do not move. Do not move. Okay, I will provide for this one. This one is the original concept for Equer 1. Looks complicated, but really it is not, because essentially we have 7 camera mounted on the pillars on the column inside the prayer hall. Then we have 3 cameras mounted on the mezzanine and 2 cameras mounted in the cour. Plus, here, 4 cameras on the minaret and 2 radio cameras that can be used only inside the prayer hall. There are no antenna available outside. So the radio camera can be used only inside the prayer hall. Then we have a video switcher, a router, character generators, some players, multi-viewer. We have all the equipment that we will see later, but normal equipment that we should have in a broadcast system. Which the element which characterize the AQR1 are the number of camera that we have installed. All the camera except for the radio camera, but all the camera from 1 to 12, including the 4 in minaret, that means 16 camera, are the same kind of camera, the same type model camera Sony. The 2 radio camera are different, but for other reason. Of course, are still broadcast camera in any way. Just to have a comparison, we can see also that one, which is the same video block diagram, but for the prayer hall. Into the prayer hall, we have 4 camera here mounted on the PTZ system and 4 camera mounted on a tripod. What does it mean? If we go back on the previous one, that one, although these camera are mounted, except for the radio camera, all the camera are mounted on a PTZ system. That means our camera in a fixed position. Of course, through the PTZ system, we can move, pan, tilt, and zoom, but the camera, if the camera is mounted on a column number 3, of course, still there. There are no way to move it. Auditorium has a different configuration because requirements for auditorium are different. And we have 4 fixed camera mounted on a PTZ system and 4 camera which can be deployed on a tripod, and you can move, of course, the tripod everywhere into the auditorium. Near the stage, far from the stage, on the left, on the right, wherever you want. Also here we still have 2 radio cameras and all the other equipment like video switcher, router, and monitors, and so on, that we will see in detail later on. AQR1, from video point of view, AQR1 and AQR2 are very similar. I mean, the differences are in the number of the camera used and in some other small differences, but the heart of the system means the switcher, router, multi-viewer, monitor, and so on are exactly the same. The configuration is the same. In these 5 days that we have to spend together to see the system, I will talk mainly for the AQR1, which is the more complete system, but the same things applicable for the EQR1 are identical in EQR2. Of course, except for the camera numbers, but of course, except for the wire. I mean, the wire number, each labels on the wire is different. But if there is one wire from one camera to the video switcher in EQR1, there's the same wire in EQR2. That means the philosophy of the system are exactly the same. So now, let's just, yeah, at the beginning, if you remember, I talk about um, uh, the SMPTA cable and triax cable. SMPTA cable and triax cable, um, in some way, we can do not interact with the EQR1 and QR2, are generally speaking point-to-point cable. We will see that later in detail, but for now we can say that outside um, the prayer hall and outside the polyvalent, there are some floor box and wall box distributed in the area, which allow us to connect camera, audio, video, monitor, in any way some services on the external areas. This is, and now I show you that one. This areas, just to have an idea, is the esplanade area. In the esplanade, we have some wall box distributed on the area, on which box we can connect a video camera, a fiber for data or video or audio or whatever. And this box belongs to the EQR1, but for fiber and SMPTE cable. In each box, we have also a triax, which goes directly from a single wall box to the TOC OB-WAN. I think there is, yeah, it's better to show you. TOC OB-WAN is in this position, more or less, which is not shown on this diagram because at the time when the diagram has been built, the position of the TOC OB-WAN was not decided already, but now is in this position here. That means the wall box which is here, I think it's wall box 18, has a triax which goes directly to the TOC OB-WAN in this position. That means if you have OB-WAN with the triax, you can connect the triax here and the camera in this position. And you have the camera directly on the OB-WAN. Any question?
No.
Okay, perfect. So let's go on. I have to switch off this one, yeah. And also this one. Okay. Now, the same philosophy can be applied to the garden. Also in the garden, we have wall box and floor box with equipped with fiber, tracks, and SMPTE cable. Uh, just to have an idea, here, where is my cursor now, there is the entrance of the auditorium, just to give you the position. So, um, we have 1, 2, 3, 4, 5, 6 wall box in the garden and 7 wall box in the esplanade. Okay, Marco, can you switch back to the slides? Okay. Um, we have now esplanade and garden, and we have also a deployment of the system inside the prayer hall here on the right and on the cour. We have 2 columns on the cour in this position, in that position.
Marco,
We have
can
a
you
PTZ system.
switch? Sorry, Maurizio.
Yeah.
Marco, he need to switch the slide, the screen.
Marco, please, can you switch to the slide?
Thank you.
Okay, thank you. In the cour, we have 2 columns, one here and one there, which Vinten PTZ system and the camera, video camera inside. There is one particular that we have to analyze about this camera and this system because for technical reason, those camera on column A2021 and on column A2116 are connected with the fiber, but instead of use a 24 core fiber, in this case, for technical reason, it has been only possible to use 12 core fiber. Each camera use 2 fiber, and that means still 10 fiber available in the wall box. Sorry, something happened. Okay. In the wall box in the column to be used for other services like Ethernet, audio, video, monitoring, or whatever. In the prayer hall, we have camera 1, 2, 3, 4, 5, 6, and 7 mounted on the column, and as we have seen before, it's a camera mounted on a PTZ system in fixed position. And in the black, you can see the number of the column. This number is the official one, which you can find also the number, this number on the building drawings. Sorry. Together with the camera, there are some other services that we will see later. But on each column, a 24 fiber core will arrive instead of 12 like in the core. We have 3 more columns, this one, that one, and this one, with the same amount of fiber which arrived there, 24, but without camera installed. That means, if needed, an external camera, maybe on a tripod, can be mounted in near wall box 11 on column A1 013, and the signal arrives. If it is a triax camera, the signal goes directly to the TOC or BVAN. If it is a SMPTA camera, the signal arrives directly into the EQR1. Or simply, just if you need it, you can install a monitor near column wall box 11 and send us a video signal from EQR1 to the wall box 11. So every time we have a connection through the fiber, um, we can consider this connection bidirectional. We can send a video from wallbox 11 to the EQR1, but also we can send a video from EQR1 to the wallbox 11. This generally is valid for all the system into the prayer hall. So next one is this one. We have the prayer hall it is divided in two levels. The RDC level, and there is a mezzanine also. Under the mezzanine, we have three cameras in a fixed position mounted on a PTZ system, Shotoku PTZ system, and we use the support of the camera also for other purposes, not only for the camera. Particularly, for camera 8 and camera 10, on the support, we have a Vis-Link antenna. Vis-Link antenna are the antenna for the radio camera. And also we have a Bolero antenna, which is for the intercommunication system through the radio intercommunication system. We will see later in detail. But on camera 9, which is, if you look at it, it is exactly in the center of the prayer hall. We still have a camera, of course, but we have just one antenna Vis-Link, which is completely different from the two antenna that we have here, because this antenna, it is the channel back. So what does it mean? Those two antenna are receiving antenna. This is a transmitting antenna, means an antenna which transmit the data back to the radio camera. So let's imagine um, the radio camera can be manual with the operator, or can be mounted on a tripod somewhere and leave it alone. In this case, if we want to control the iris of the camera, not position are not PTZ camera, but maybe the iris, which does it mean the luminosity of the camera. There are two ways. Or manually, someone goes there and move the iris manually, or using this back channel, the camera can receive the information from the EQR1 and adjust the the iris according to the RCP settings. Sorry, just a minute. So the next one, okay. If you remember before, we have seen uh, there are some column into the prayer hall. At the base of the column, we have a plate with some connection. Of course, power is 220 power, no problem to supply power to the equipment. But we still have a triax which goes directly to the top of the van, SMPTE which arrives directly to the EQR1, and um, MTP12 which is an optical connection, 12 fiber optical fiber connection, and two optical double optical, two fiber here and two fiber here to the EQR1. Uh, any connection on this plate is independent from the camera connection mounted on the column. So in other words, what does it mean? You can destroy completely this plate, but the camera mounted on the column still working, because these are additional connection not related to the camera on the column. On the base of the column, at level S10, there is a column box which receive the fiber from the EQR1 and connect this fiber to the plate, and also inside here there is also power supply for the camera on the column. So if one camera on the column still appears not working for some reason, may be possible that we have a fiber problem or a power problem. If the problem is the power, please check into the column box. The next one show you which is the EQR1 CR1 position at the level S10 against two wall rack 2 and wall rack 1 here, located at S10. Those two wall racks are very important because they contain some electronics like DMX distributor and Ethernet switch for Shotoku controller. So DMX distributor is a distributor for the control for a signal which control the light. On each column we have two lights, Harry LC7 scene lights, and these lights are controlled through DMX protocol. It's better if I show you the schematics. Let's see, okay. Marco, can you switch the... Okay. Let's check first Warrack number 1. Okay. In EQR1, we have a light console, which is a controller for the light. The output of the light console is a protocol, a DMX protocol, which goes directly to this distributor, which is located in the wall rack number 2. So the DMX distribution amplifier takes the signal and send it to the light directly on column um, in pre-roll. But one of the output of the DMX distribution amplifier goes back to distribution amplifier located into the wall rack number 1, and this one allow us to control the light for camera from 1 to 4. This is an equipment which is installed into the wall rack. Um, why we have a distribution system? Because even if we can do distribution of DMX through a loop system, um, Marco, stay here, please. I have to use this one. Let's have, imagine that we have, oh, sorry. We have, this is Harry light system, okay? And we have a DMX, oh, sorry, signal which control the light, control the intensity and the color, of course. DMX protocol is a sort of the RS485 protocol, serial protocol, in which we can assign to each light a number. Maybe this is number 1, number 2, and so on. Then we can loop the light through the DMX. But if we do that from light 1, we have 7 column, 2 light per column means 14 lights on 7 column. The problem is that if we distribute the DMX through the input and output on each light, the total length of the cable exceed the maximum distance. So that means we are able to control light 1, 2, and maybe 3, but light 14 we cannot control it. This is the reason why we have used an N-Tech distributor which receive DMX and regenerate, because there is a regenerator here, and send this cable just to one light. This is a way to overcome the distance problem. Yeah, let's go back here. Together with the DMX distributor inside the column, as we have seen here. We have also okay, a fiber which arrives, and just two fiber are used, all the other are available to, and they go to a switch. Why there is a switch here? This is the secondary channel or backup channel for the robotic on the column. The robotic on the column, robotic means PTZ system, which move the camera. Each robotics has two Ethernet link. One is the main link, and the other one is the secondary or backup link. If the main link will fail, you still able to control the robotic through the secondary system, which is through this two Ethernet switch. Now let's go back. Marco, please, can you switch to the other? Yeah. Any question about?
S'il y a des questions, même en arabe, pas de problème.
Sorry, I can't hear anything.
There is question. 1 second.
There is question.
Maurizio, please, could you go back
Yeah.
to slide number 8 about the Vislink antenna?
Okay. I'm going. This one.
Yes. I want just to understand why the antenna aren't in the same position and how we control the signal inside the prayer room.
So you mean why there are two antenna here and two antenna here?
No, the transceiver and the receiver, they aren't in the same position. Why? And how we control the signal inside? Because it's a different area.
No, sorry, but I have not understood. I mean, there are two antenna on camera on the support of camera 10 and two antenna on the support on camera 8. Okay.
Yeah, you told us that those both are receiver.
Camera, these two antenna are receiver. Yes, two receiver antenna.
And
Yes.
the other in camera 8 are receiver too.
Camera 8 are receiver too.
Yes.
Yes.
Camera 9 are transceiver, not receiver.
Is transmit.
Yes. So they
This
work
one is
with
a
the
transmitter.
same,
Yes.
with the same camera.
But yeah, maybe I have understood. In the next slide, we will. In the next day, we will see that because this one are a receiver or over a range of frequency from 1.9 to 2.7 gigahertz, and this one is a transmitter at 433 megahertz, which is data back. This does not transmit video, just data.
Okay.
In the next day, maybe tomorrow, if I remember well, we will see that how it works. There are two antenna. Oh, sorry. There are two antenna here and two antenna there because the system works on a diversity functionality. That means we have two radio camera, and with that system, if you walk from this position to that position, Of course, in this position, your signal will be received by this two antenna, and along you move, this signal will decrease on camera 10 antenna and will slowly increase on the antenna mounted on camera 8. Automatically, the system decides which is the better signal to receive and automatically make a choice, but you have a video and audio, of course, continuity on the output.
Maurizio, please, this is my question. For example, if the camera is in the member, so the signal from the transceiver, not the receiver, will be decreased. How we control that?
For the transmitter?
Yes.
Oh, we make calculation for the distance. There is no problem. You send only small data for the iris,
But
the open, the
coverage,
filter.
the coverage. One antenna
Yes.
can cover all
Can
the
cover, yes. Because he sent small
Oh, you mean
data.
that? Yes, yes. Because this transmitter can be controlled from 1 to 5 watts output.
It's not the same type. This is why Walid asked,
No,
I
it's
think.
completely different.
Yes.
And at the minimum power that we have now, which I think it's less than 1 watt, we can cover the entire area.
Perfect. That's what I want to
Afternoon,
understand.
we can
Thank
see
you,
it, I think, Maurizio.
Yeah, please, Omar, in the afternoon, if you want to show him
I think
how
now,
it works.
Now here they can see the white antenna there. If you can see it on the balcony, is the receiver. Is a type. The other one is with camera number 3 here. Is a very small one, the transmitter. Just here, you cannot see it from here, but afternoon I can show you better.
So for transceiver and the receiver, they didn't have the same area coverage?
Yes.
Okay. Thank you.
Omar, the same antenna you have on at the top of the auditorium, near camera 4, I think.
Yes.
You cannot see it, but it's a very small antenna that can cover the entire auditorium.
When we finish, I show them the antenna. From here, you cannot see
it. Remember that the two systems, they work at very different range frequency. The frequency receiver for the video camera is from 1.9 to 0.7 gigahertz, and the transmitter data back channel is 400 megahertz, are completely different. Other question? Sorry, I can't. There are other questions?
It's okay, Maurizio, you can continue.
Okay, perfect. Okay. Okay, we have seen. So now I want to spend few words about the drawing system and numbering. I know that it is not such important things, but in your hand you have a manual, and into the manual I follow this technicality to describe the drawings. This is why it's important to know how it works. So each drawing has an official number or name, like 7 EAQAS and so on. Of course, this is an official number to store the drawings according to certain rules. But from a technical point of view, it's too difficult to use it. This is why we have decided to use an internal numbering system, which is easier to understand and easier to remember. The internal numbering system is composed by first S or P, where S are all the drawings, technical drawings, schematics related to the pre-roll and associated areas. So, pre-roll, Taco Bivan, Bat M, Esplanade, Garden, Cour, and level S10. The drawings which start with the P are related to the auditorium or polyvalent hall and associated area. That means EQR1, EQR2, CR2, auditorium, edit suite, archive, and backstage. Sorry, just a minute. So, um, there are a small details which is represented here. When you find the drawings with the internal numbering system, which is S.009 dot something, maybe dot 1, 2, 0, 3, 11 or whatever, means that this drawing, it has been divided in multiple drawings because was not possible to fit it in one. For instance, I think drawings for Ethernet is from S009.0 to S009.11 or 12. If the drawing is S.00, a number without decimal point, that means it's only one paper. There are no other drawings related to it. Question? Hello?
Now you can continue.
Okay. Uh, in the manual, the major part of the drawing are related to the internal numbering system. And then we have the cable numbering system, which is divided in two parts. One part is the class number, and the other part is the number itself. So the class number is, in other words, a system just to uh, give a name to the cable and in which allow you to understand this cable is related for. Maybe 02 is all the cable that goes from A1 in EQR1 to the bâtiment M. So that means all the cable from EQR1 to the bâtiment M have a class 02 at the beginning. And the same things can be explained for the other. In the manual, there is a complete description, of course. I think it's page 36. Even with the cable numbering system, when we have seen which is the area involved, maybe in EQR1, bâtiment 1, or EQR1 minaret, EQR1 something else, we have to give to the cable a numbering system. Uh, and this is a very important feature because according to the numbering system, we can see which kind of a cable is it. Maybe if the label range is between 0 and 999, we have all the analog video and RF cable. If for a total of 1000 cable, so that means inside in the entire system, we cannot have more than 1000 cable for analog video and RF system. For digital video, which means HD, 12G, or any kind of digital video, we have a numbering system from 1000 to 5000 more or less, which means 4000 cable, and so on, of course. Uh, These color are just a reference for the cable list, not for the drawing. Drawing, the color of the cable into the drawing is a different, follow different rules, but this one is just for the cable list. So now let's see some example how to read the cable label. If you take one cable, any cable, you can see that there is a label on it. Okay, uh, maybe cable 20-0013. Class 20 means a cable which is inside EQR1. 20 means EQR1 to EQR1. Maybe a cable which comes from rack number 1 to rack number 5. um, the 0013, if you look back, this one, 0013 means it's an analog video or RF cable. This is what just the label says about this cable. If you go on the cable list, on the table for the cable 20, you can find that it is a generator reference out number 3 to the video switcher reference in. More in detail, if we have a cable 027001.1, so 02 is a cable from EQR1 to the bâtiment M. 71001, 7 means fiber, can be single mode or multi-mode or hybrid, but it's a fiber. And 7001.0 means this is a multi-core fiber. So Marco, can you please switch to, yeah, in this position? So now if I do that, it's better. Okay, now this one. Okay. Oh, sorry. Okay. Let's say this is our fiber. And inside we have a single fiber which are called core. As I told you, we use normally 24 core fiber. So that means inside um, a fiber cable, there are 24 single fiber. Of course, we need a way to number this core, and the way is 0270001.1.0, sorry. This is the number of the entire cable. 0270001.1, this is the number of the first core. Then we have 2, then we have 3, then the last one will be 24. It's like to say this is a family name and these are the single name of the component of the family. Of course, if we have 24 core, but if the fiber is just 8 core, what we have is from 1 to 8. The same numbering system is used for the audio cable. Now I show you. For some audio cable, we have, oh, sorry. For some audio cable, we use a snake audio cable, which is an audio cable with, in our case, 8 audio cable inside. Also in this case, we use a family name for this one, which is maybe 03 dot something dot 0, and 1, 2, 3, 4 up to 8 are the number of the cable inside. Is it clear? Any question? Hello? Hello?
It's clear, Maurizio. Thank
Prosegua.
you.
Okay. Okay. So let's go on the next one. Marco, please, can you switch to the slide? Okay. Now, here we have some example of the cable. And if you look at here, we have multi-core optics fiber, which it is was, I told you just before, about the number of the core inside. And audio multi-core cable is this one, and which is called a snake audio cable. This is DMX cable. If you remember, we have already saw that one about the DMX controller. In the typical DMX cable has 4 conductor inside, which is ground, this one, plus 2 conductor shielded, and 2 bigger conductor here. But the standard provides that just 2 conductor are enough to send and receive DMX data, plus the shield, of course. In DMX system, in GMA, we have a cable with 5 conductor, but we use only 1, 2, and ground. And then we have a triax cable. So why we have 2 different type of triax cable? The reason is a way of a sort of mechanical decision, because one cable is triax 11 millimeter. 11 millimeter means the diameter of the cable. The other one is 14 millimeter, which is bigger. 14 millimeter cable allow you to reach a long distance. And 11 millimeter allow you to have a short distance, but you can pass through the pipe in the wall. So the 14 millimeter has been used for a long way on from one point to another. But when you have to get back into the wall to reach a position, then this 14 millimeter has been joined with 11 millimeter, and the 11 millimeter is the last part of the cable which reach the floor box or the wall box. It's better if Marco, can you switch to the other side? Okay, let's imagine, sorry, as usual. Yeah. Yes. Just a second, please. Omar. Omar.
Yes.
Omar.
Yes, yes.
Yeah, please tell me. If you want to do a break, we can do that now.
But what time you start after run break?
Break for 10 minutes or?
Yeah, I don't know. Ask them.
Est-ce que vous voulez faire une pause de 10 minutes ou là on continue? Hein? Maurizio,
Sì?
quanto è rimasto quanto tempo è rimasto per il primo giorno?
Dovremmo smettere alle 12:30.
Ok, nous on a programmé de finir la première journée à 12h30. Ça vous va? 12h30? On continue? Pas de pause? Ok, allora facciamo una pausa di 5 minuti.
Va bene.
Okay. On fait une pause de 5 minutes. 5 minutes.
Ciao Maurizio. Do you hear me?
Yes, of course.
We can continue. Everybody's
Okay,
here.
perfect. So I have prepared this drawing, as you can see, just to explain exactly what happened with the triacs. So let's imagine we are in the talk, and then we have the terminal panel for the triacs, which is here. Then we start with 14 millimeter, and when we goes at S10 on uh, the cable here, and on the cable trail. And of course, the cable trail is free. I mean, you can use any diameter you want here. There is a lot of space. But maybe when you arrive in the garden, and then you have to go into a pipe. This is a pipe which goes into the wall to get out front into the wall box in front. Then into the pipe there is no such big space for 14 millimeter cable, especially if the pipe is not straight but you have to do some curve. Here we have a junction from 14 millimeter to 11 millimeter, and the last part of the path is doing in 11 millimeter, which has a diameter um, lower than 14 millimeter. So the long distance is performed with 14 millimeter. The short distance is performed with 11 millimeter. Is it clear? I can go on?
Yes.
Okay. So, Marco, can you switch to slide, please? Okay. So here we have some kind of connector used into the GMA. Tracks, cable, and connectors we have already seen here now. I want to point out, well, we have micro BNC, BNC traditional, audio jack, XLR audio connector, that's it. Are very normal, even the SFP optical LC. What is, I want to point out the SFP BNCs, the dimension of this SFP are identical. But in one case we have optical interface, and the other case we have coaxial interface. And this coaxial interface use micro BNC. This is very important because in router and multiviewer we use micro BNC in EQR1 and in EQR2. And I want to point out also the audio patch connector, which is called Bantam. Bantam is a name of a brand that along the years has been a name of a connector, generic audio patch connector. Please take a note about the three sections that we have: sleeve, ring, and tip. Sleeve is a ground, ring and tip are signal. Later on we need this description to understand the patch panel. Um, these are electrical connector, and the next slide show you the fiber connector. We use all of sort of fiber connector. There are two important items. One is MTP12, which is a panel connector for NTP12 connector cable, which is this one. So as you can see in this connector, very small one, we have inside 12 fiber. There are many combination or standard. We use this one on which from the MTP12 to LC we have um, position 1, position 12, position 2, position 11, 3, 10, 4, 9, and so on. We will see later what does it mean. There is another standard which says position 1, 2, 3, 4, 5, 6, 7, and 8. We do not use that. We use position 1, 12, 2, 11, 3, 10, and so on. The other connector are standard. What I would like to point out is the SMPTE connector. So those two white pins are the fiber, and these two are the power. Be careful. Marco, can you switch please on the whiteboard? Yeah, thank you. Be careful because let's talk first about the SMPT. Oh, sorry, as usual, yes. SMPTE cable goes from BPU to camera. Can be 100-meter or 1000-meter. But this SMPTE cable has a data connection which is fiber. So video and eventually audio will travel through the system on a fiber, but the BPU supply power also to the camera. And the power is between 170 to 200 DC volt. Uh, there are many protection systems inside. Maybe if you disconnect the camera, the PPU goes in alarm. And cut the power. That means this one has been cutted. Or if you disconnect the BPU, of course the BPU goes in alarm itself. Off. If the cable, there is a short circuit, the BPU will goes in off. But if everything is working and for some reason you goes in contact with the inside power, will be dangerous. The cable is shielded, and to go in contact it's very difficult, almost impossible. But it's better do not cut the cable when the system is in operation, always. And here we have a male, and here we have a female, where those two are the fiber, and this one are the Sorry, this and this one are the fiber, and this and that one are the power. The same version of the connector exists for the cable. These are for panel, and these are for cable connector. So let's go on the next one. Yeah. Here we have a different type of, sorry, of MPO. Yeah, it's better. Marco, can you switch on the other, Marco? Okay, thank you. Um, we call it MTP, but NTP is just a name. The family is MPO, um, where MTP is a certain type of MPO. We use MTP 12, but exists also MTP 24. We don't use it. We use MTP 12 connector, but in this case, can you switch back, Marco, please, to the slides? Okay, thanks. In this case, we have a particular version of MTP12, which can call it MTP8 in some way, and it is used by this kind of SFP, which is used, which is called QSFP. Instead of using 12 fiber, this kind of QSFP use just 8 fiber and are used in this way. From 1 to 4 are TX fiber, and from 9, 4, 5, 6, 7, 8, 9 to 12 are RX fiber. And the cable is 1, 12. So 1 means that one. And LC number 2 here means the fiber comes from 12. 2 is that one, and 11 is this one. 3 is this one, and 10 is this one, and 4 is this one, and 9 is this one. If I show you the slide before, we have the same cable, but with 12 fiber used. That means the also the fiber here are connected, where we have 5, 8, and then 6, 7. Here we have 5 and 8, and 6 and 7. We use both this kind of cable and this kind of cable, but this one NTP8 is used only in Riedel product, which use this QSFP. Riedel product use 4 QSFP in that position, and that position is connected with this kind of a cable. It's important to notice that each, if you consider 1 and 12, from technical point of view, this is called one link. And one link has the capacity to have 25 gigabit per second. That means if we use 4 QSFP, each SFP has 4 link. That means we have a total of 4 QSFP for 4 link for 25 gigabit, a total of 400 gigabit seconds, the throughput from the Riddle product. We will see later how to use this large bandwidth. We have also audio and video patch panels, uh, video patch panel with 32 position on 2 different rows, and the audio patch panel with 48 position on 2 rows. In this case, we have 64 position a total, and in that case, we have 96 position in a total. The patch cord are different, of course, because the nature of the signal is different. But in both cases, we use patch cord to give more flexibility to the system. About the flexibility, we have a patch audio, and the identification is doing in this way. Row A and row B. Doesn't matter if we have a video or audio patch panel. We have row A, row B. So the label now is V1 means video 1, video patch panel number 1, A row, which is the upper one, position 010. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. This position here is position 10. If we, the same thing is for the audio patch panel. A1, A means audio, 1 patch panel A1, row A, position 042. So if the patch has 48 position, 42 is more or less in this position here. This is the way on how to give a label to the patch panel. Labels to the patch panel are important because on the schematics, each patch has its own label and its own cable which is connected to that position. For the fiber patch, we have used upper and lower position, up and down, and numbering is 1 up, 1 down, 2 up, 2 down, and so on. Of course, this kind of numbering is also on the schematics. For the Ethernet patch panel, we use 24 position, and the Ethernet patch has 2 different point of view. This one is the external, so is what you see on the patch panel mounted into the rack. But of course, on the rear should be some cable which arrives to the patch panel. The connection on the rear are called the tie, and the connection on the front are called the port. PPA's patch panel Ethernet 06 port 17 means port 17 on the front, this one. PPA 09 means patch panel 09 tie 18 means the rare position number 18. So should be this one on the rare. This is what we have called. Be careful, we use often terms like tie lines, tie lines, T-line, trunk line. In GMA, all these words are synonymous and will indicate a connection available to transport a signal without any direction. Can be from A to B or vice versa. Is not necessarily a TX or RX. It's just a piece of wire or a fiber optic which goes from one side to another. If you want to use as input or output, you can decide basically on what you need. Okay? Some question? Omar, I can continue?
Yes, please.
Okay. And now we have a big chapter, which is the normalization. We have normalization on audio patch panel and on video patch panel. Let's start with the audio patch panel. There are many different kind of normalization, but we use this one, full normaled, only this one. What does it mean? It means that if I connect a cable on the rear here, from electrical point of view, without to insert anything here, I have a continuity from upper position to lower position. This electrical continuity is obtained by this contact that you can see here. Let's imagine a signal comes here, goes through this cable, goes here and appears in position here. Where SRT, if you remember what I told you before about the connector, is a sleeve, ring, and tip. If I go back, sleeve, ring, and tip. When you insert this connector into the audio patch panel, this type, this electrical contact will be connected to sleeve, ring, and tip. But what happens if I insert a patch cord here? It happened that this one and that one will be moved upward. They goes up, and this one will be broken. So the signal which comes here goes to the connector inside, it goes outside, but it is disconnected from the lower part. This means in a patch panel for normal LED, we have a continuity, electrical continuity from the upper part to the lower part. But if you insert a patch cord inside, this continuity will be broken. And the signal goes from internal to the patch cord. Even if you insert the patch cord not here but there, if you insert the patch cord in the lower position, This one will be moved upward. This one will be moved up. This contact will be broken, and then the signal which comes and arrive here is not able to reach this one. But this one is in contact with the connector inside. For this reason, normally the patch panel are used in this way. The upper part are always output and the lower part are always input. Uh, Marco, can you switch to the whiteboard, please? Okay, thanks. Now, if I do that, let's imagine we have, uh, I don't know, maybe uh, audio player. Okay, and I have the output. The output goes to the patch panel, and then I have normally the audio goes out in this direction, arrives to the patch panel, is normaled down, and then this one goes maybe to I don't know, a speaker. And then we can listen the audio which goes out. If I insert a patch cord here with tip, ring, sleeve, this connection will be broken. Then we cannot listen anymore the audio on the speaker, but the audio comes out from the uh, patch cord inserted. Maybe here I have another patch panel with the lower part is connected to another speaker. If I connect this one to here, I just transfer the audio from this position to that position to another speaker. In this way, if all the signals are faced on a patch panel, sorry, I have some fixed configuration due to the normalization. Without any jack inserted, any patch cord inserted, audio play goes out here. But if I need to modify to have more flexibility, I can use a patch cord to send any signal in any position according to the fact that any position is interfaced on the patch panel. Generally speaking, in GMA we have used a lot of interfacing through the patch panel to increase the flexibility of the system. We have some fixed configuration, but if you need to do something special or something different, it may be possible through the patch panel system. Uh, Marco, can you? Oh, no. Yeah, switch please on the slides. Okay. Okay, because I have to add something. Of course, this normalization has been done internally. into the patch panel. From external, you cannot see it. Then the problem is how to recognize when the system, when the position of the patch panel is normaled or not. This is written on the label of the patch panel, where on the label, if there is this small square, means this position is normaled with the lower one. In this case, this radio channel 1 goes directly to the QL5, which is mixer, video audio mixer, sorry, input 1. It's normaled. I mean, we have not to use any patch cord. Automatically, this output goes to this input. In this case, there is no indication here. That means this output is not connected to the Tascam left in. If we want to have this vertical connection, we have to insert a patch cord here and a patch cord there to connect the upper position to the lower one. This is on the front of the patch panel. Into the schematics, position normal LED are indicated with sorry position normal LED are indicated with this small arc over the patch panel. Position V3, this is in this case is a video patch panel. Video patch panel number 3, position row A, position 05 is normal LED with the position V3B05. In that case, V3A7 is not normaled with B07. So if I want to have a video from this position to that one, I have to insert a patch panel. Sorry, a patch cord. Any question? Hello?
You can continue.
Okay. The same thing, video patch normalization, can be seen also on the video patch panel. Video patch panel follow the same rules. All the output are on the upper row, all the input are on the lower row. So we have this video patch panel normal LED, and we have also which is double view type, and we have also S type, which is this one. Double view, which means normal, is indicated with the underline on the patch label. The S-type without normalization is indicated without the underline. In this case, this video out 08 goes to the multiviewer in 16, multiviewer 2 input 16, without any patch cord inserted. In this case, 09 out is not connected to the lower position, which is free. But let's assume that at a certain moment I want to see, instead into the input 16 of the multiviewer 2, instead to have 08 out, I want to have 09 out. Simply, I have to connect a patch cord here, which goes to there. In this way, This output is cut it, and the video goes from this position to that position. This is represented clearly in this phase. Without any patch cord inserted, the upper position is connected to the lower one. With the patch cord inserted in the upper position, the video which comes from here goes to the patch cord directly, but it is disconnected from the lower position. Even if I connect the lower position, the video comes from the patch cord that goes inside. Maybe this lower position can be this one, multiviewer 2, input 16. If I insert a patch cord here, the upper position, 08, as you can see, is cut, and the signal which goes input the multiviewer to position 16 is the signal which comes from the patch cord. And if the patch cord is connected to position 09, which is this one, we can assume that here, we have connected this one to that one. So exactly what we have seen, we have already seen for the audio, also for video, using the patch cord give more flexibility to the system. But why we use also S-type, this kind of connector? Because there are some cases where the upper position should not be connected automatically to the lower position. In this case, we have to use a straight through type, which is S, in which we can connect any signal here, but the two devices connected in upper position and lower position are not never connected together. Well, if I connect an external patch cord, yes, but in normal condition, they are not connected. This allows us to do a small tricks, which we can use the upper and lower position both as output. So in this case, we are forced to use the upper position as output and the lower position as input. But if there is no electrical connection between the two positions, I can connect an output here and an output here, or input here, another input here. With this increase the density of the system, we have to use a less number of patch panel, and it is an optimization of the system. Any question? Hello?
It's okay.
Okay, good. About the fiber patch panel, we have seen already there are 24 position and upper and down position. With 24 position times 2 means 48 fiber for each panel. But we have also a different kind of fiber terminal, which is this one is a panel which is in EQR1, and you may see this afternoon, and each one is composed by optical MTP12, where inside there are 12 fiber, and optical duo with 1 and 2 1 and 2 fiber. This panel, just this one with MTP12 optical duo and optical 1, optical duo number 2, comes from wall plate, floor box, and wall box, which are spread into the system: garden, esplanade, wall plate on the column, and so on. So if I go back here just to show you, okay, this wall plate, this optical MTP12 and optical duo are on a generic column base, are terminated in AQR1 on this fiber panel. And this is valid for the column and the floor box, which are around into the GMA. That means all the optical connection are from a floor box to the AQR1. Not directly, of course, but from, sorry, what happened? Okay. Okay. From floor box, wall box, and so on, the optical cable will arrive first on this kind of device. This is the main entrance of the 24 core cable, and then from the other side we goes to the panel here. These are called fiber junction box. On the rear rack 2 in AQR1 you can see a lot of this. Maybe this afternoon Omar or Marco or Rashmi will show you. And then we have some connection box or in Esplanade Garden, where we have also optical duo, which arrives to the AQR1 we have already seen there. Oh yes, this is a different type of connection. So let's consider this SMPTA connection, or give me a second, I have to reach, or this one on the wall plate. Means that there is a SMPT cable connected here, which goes directly from a wall plate and the column base to SMPTA terminal block on the rear of the rack 5 and 6 in AQR1. If you go there, you can see 3 boxes with SMPTA termination there. It's a point to point from wall plate to this wall box, from floor box in the garden to this point here. Why we need it? Because we have 2 possibilities. The first one is, well, I want to install an SMPT camera at the base of column maybe 14. If you remember at the very beginning, I show you No? Okay. Maybe if we are in the column wall box 11 in the prayer hall, we have no camera mounted on the column, but we have a wall box 11 at the base of the column, which is called a wall plate. And on the wall plate, there is an SMPTE connection which goes directly to the EQR1. Goes maybe directly here. That I cannot read the name here, but maybe let's imagine arrive here. That means I can connect a camera on wall plate 11 on that column, temporary, of course, on a tripod. And from this position, I can connect this camera to a BPU which is inside in rack 5 and 6. Of course, I lose one camera from the column, but I have more flexibility because it's like to move the camera which is on the column that I don't need to on another column that I need it. We have 7 connection to the esplanade, 6 on the garden, 2 on the minaret, and 14 in the column plate on the prayer hall. It's a point to point. Is it clear? Hello?
Yes.
I can continue?
Yes, please.
Okay. Okay. Okay, what time is it? Oh. Give me a second, please. Omar. Omar.
Yes.
Hello?
Yes, Maurizio.
Yeah, listen, R1229. I can continue until 1 o'clock or I have to stop here? Because we have started 1 hour later. 1 hour, we lose 1 hour this morning.
نكمل حتى الوحدة ولا نحبسوا؟ وش رايكم؟
Maurizio,
Sì,
possiamo staccare per pranzo?
e vuoi riprendere nel pomeriggio?
Nel pomeriggio, un'ora.
Allora,
Non so se è fattibile
fammi
per te.
vedere. Questo, allora, per me sì,
Ah,
nel senso che io non ho grossi problemi. Sì, servirà un'oretta oggi pomeriggio probabilmente.
mm.
Quindi non so, ditemi voi, per me
No,
va bene.
disponibilità tua
Io sono disponibile, certo.
a partire dalle 2?
E dimmi te, non lo so,
Le
io non
2
ho
sono
problemi.
già, sì, le 2, fra un'ora e mezza. Perché sono arrivati un'ora in ritardo.
E sì, infatti era calcolato, cioè avremmo finito giusto, capito?
Ok. Donc, ok. Tu sei d'accordo?
Io?
Oui.
Sì, per me va bene.
Ok, donc, alors,
Facciamo un'oretta oggi pomeriggio
si,
e poi
alle
facciamo
due.
la visita
Si.
alla QRU.
Alors, on va finir l'heure que nous avons perdue ce matin à 2 heures. On va se rencontrer ici pour finir la séance d'aujourd'hui, hein. Et tout de suite après, on va faire des visites sur chantier à 2 heures. Le temps de manger. Ok, ça vous va? Ok, ok, Maurizio.
A che ora quindi riprendiamo?
14.
Alle 14. Va benissimo, d'accordo.
Guardiamo, andiamo. Guardiamo. No, no, andiamo. Ok, grazie Maurizio.
Grazie a te. Ok, a dopo allora.
A dopo.
A dopo.
Buon appetito.
Rafik, sei in sala?
Sì, ci sono.
Ascolta, cosa faccio? Comincio o aspetto?
Allora, io direi di cominciare. Quello che c'è, quello che non c'è, non c'è,
Va
diceva.
bene,
Eh,
va bene, va bene.
ok.
Ok. Marco? Ok. Sei in registrazione? Ok. Ok. Okay, we can start this second session now. And we have to talk about some video standard that we use in GMA. Essentially, we use two video standard different. One is 12G, of course, which means a resolution of 4K, and the other one is HDTV with the standard HD resolution interlaced. The 4K, it's always progressive. HDTV can be progressive or interlaced. In our case, we have HDTV interlaced and 12G 4K progressive. The number that you can see here, 3840 and 2160, are the horizontal pixel and vertical pixel visible. So with this number, we are talking about the real dimension of the picture. In reality, there are more pixels, but are not visible. These are, when we talk about 4K and also HDTV 1920 by 1080, it's always the visible picture. 12G is progressive. HDTV in our case is interlaced. It can be also progressive, but in our case, for compatibility with the national television, we use interlaced. Is not a matter of choice which standard use, because the system works at the same time in both standards. So the main output of the GMA EQR1 or EQR2 are always present at the same times in 12G and HDTV. Main differences, except of course for the resolution, it's that the 4K 12G works in high dynamic range, and the HDTV works in standard dynamic range. That means the high dynamic range allow us to have a more space between black and the maximum white. If you have more space, you have more gradation between black, gray, light gray, and white instead of the standard dynamic range, which is more compressed. Of course, this expansion of the dynamic range does not relate only the gray level, but also the color level. Are two different standards, and in our case the 12G works with a dynamic range model which is hybrid log gamma. There are many standards for the dynamic range, and we make a choice of hybrid log gamma because it's the more compatible standard between 12G or 4K and HDTV. So in other words, the main output is always 12G. Then we have a Sony processor which converts from 12G to HDTV, but does not convert only the resolution in terms of pixel, vertical and horizontal pixel, but also will convert the dynamic range. And the hybrid log gamma, it's the best compromise between the 12G 4K dynamic range, high dynamic range, and HDTV. 50p means 50 frame per second progressive. That means what? If we imagine we have 2160 lines in one frame. Okay, the system first write line 1, then line 2, then line 3, and so on up to 2160. And each line contains more than 3000 pixels. It repeats this scan 50 times per second. So we have 50 complete frame each second. In HDTV, 50E, which means interlaced, we have 50 fields per second, where a field is a frame divided by 2. It's half a frame, and is used to be line 1, line 3, line 5, line 7, then line 2, 4, and alternate. Then we have 50 fields per second instead of 50 frames per second. Of course, the resolution is lower because we are working at 1920, but also the field rate or the frame rate is half because 50 fields per second means 25 frames complete per second. It is important to understand that these numbers are only relative to a divisible picture. So the next slide show us some details about that. In the origin, in the first, if you look here in that position, we have the old PAL system, which was 720 576 line and was interlaced, was a standard definition. The aspect ratio was 4:3, which almost square, but this kind of standard has been deleted now because the pixel shape was not square, was uh, 1 divided by 1001, which is what was rectangular. With the advent of the computer and the video on the computer, uh, the computer itself, the picture on the computer itself, the menu, is written with a square picture. Square pixel. The aspect ratio of the picture of the pixel is 1 by 1, and can be interlaced or progressive. On the computer is always progressive. Along the time, we had a convergence between what was the traditional video and the computer, and everything has moved to the video from computer, which requires square pixel and the resolution, typical resolution of the computer. We have now screen, of course, visible picture, which is 1920, 1080, which is aspect ratio 16:9, more or less 2 millions and something point per picture, per frame, sorry. In the other step has been transformed to 3840, which is what we call 4K, which has approximately 8 million pixels for frame. So every time we move from one to another, the dimension of the picture increased by 4. If you look at here, this line for the using this line as a reference was 1 for HDTV. For 4K is 2, means the dimension of the screen is 4 times more. We will see that better in the next slide. What we can see here, it's the aspect ratio is from starting from 1.2 up has been always kept 16:9, except for cinema, and we will see in the next slide, which is more rectangular. If we divide the total number of the pixel, here we have also a different resolution, which is 8K, which is about 33 million pixels in one frame. And if you divide 33 million divided by HD, you get 16. If you divide 33 million divided by 4K, you get 4. This number 177 simply means that the aspect ratio is always 16:9, as you can see here. In the next slide, sorry, why it didn't work. Okay. We have some magic number because the question is, okay, we are working at 12 gigabit, but where does come from this number? Why 12 gigabit per second? Essentially, the starting base is always HD, And in HD, we have the luminance one step back. Marco, can you switch to the whiteboard, please? Okay, thanks. So let's imagine this is a video camera, okay? The video camera always has 3-channel output, which can call it R, G, and B. Each channel is full bandwidth, but usually what we can do is a processing to get luminance output and 2-channel colored color difference. This one is called R minus Y, which means red minus luminance, and the other one is called B minus Y. The important thing is that R minus Y and B minus Y are not full bandwidth, but they can be half bandwidth. And if we reduce the bandwidth, we reduce also the data rate. This is very important because the luminance channel should be sampled at 74 megahertz, more or less, point something, 0.25 megahertz. Sorry, it's better to delete and write again. 0.25 megahertz. But the two different color difference, the 2-channel which contains color difference, can be sampled at 74.25 divided by 2. That means at 37, more or less, megahertz. This is very important because let's consider HD signal. In RGB, we have each channel is full bandwidth, and for each channel we have 74.25 sample per second. For each channel, that means this number must be multiplied by 3, which is an enormous number of bit. With the color difference, we have 74.25 sample per second and 37.12 sample per second for one channel and 37.12 sample per second for the other channel. So the sum of this one give us 148 megabit. Now, Marco, can you switch please back to yeah, good, very good. So Now, 148 megasample per second, and each sample is coded with 10 bit. It means 1.4 gigabit a second. This is why the HD signal is called 1.5 gigabit per second at 25 frame per second in progressive mode, or 1. Gigabit second at 50 field per second. Does not change, because instead of count the frame, which is composed by 2 field, we count just the field, but the data rate still 1.5 gigabit per second. Of course, if we have, instead of 25 frame per second, we use 50 frame per second progressive, the data rate is double, because we use 1.5 multiplied by 2, and this signal is called 3G. There is an intermediate level which is sometimes used, not very often, but sometimes is used, which is the 4K but at 25 frame per second. Of course, this one is called 6G. And the last one is the signal that we use in GMA, which is the aggregation of 8 time 1 gigabit second, or 4 time 3 gigabit, and it is called 12G. Here you can see in detail. 12G is 2.97 gigabit per second times 4, because we use the basic rate, which is 3G, this one, multiplied by 4, and we get 12G, of course. One of the key points of this representation is that, okay, if we use fiber to transport digital signal, generally speaking, there is no problem. But as we have already seen this morning, when we use copper coax cable, it can be a problem, because if you have a cable, more is the distance between 2 points, and more difficult is to transport one video sorry from one side to another. From a technical point of view, the manufacturer of the cable does not give you the indication about 3G, 6G, 12G, or HD, or whatever, because a coaxial cable does not mean that it must be used for video. Coaxial cable is just a coaxial cable that can transport a sort of high frequency. It doesn't matter if the high frequency is a sinusoidal or square wave or triangular wave or whatever. What the manufacturer of the cable give you the characteristics of the cable measured in sinusoidal mode. This is important because for GMA, for instance, we use VK70. Marco, please, can you switch to the whiteboard? Okay, thanks. So we use VK70, which is 75 ohm, which is 75 ohm characteristics impedance. We use it for video, but also for RF, for the video camera, the wireless camera. Because it's just a coaxial cable. And this is the reason why, please, could you switch back to the slide? This is why the manufacturer of the cable give us this value. So for HD at 1.485 gigabits per second, the fundamentals in sinusoidal mode is 750 megahertz. For 3G is 1.5 gigahertz. For 6G is 3 gigahertz, and for 12G is 6 gigahertz. And the manufacturer give you the information about the attenuation of the cable for maybe 100 meter or 1000 feet, measured in terms of attenuation at certain frequency. It says maybe, please, can you change it to, okay, they give you a number for 100 meter. You have at 6 gigahertz an attenuation of 35 dB. This is the value that they give you. Of course, if I know that my device can detect a signal until 30 dB, 35 is greater, then I cannot use 100 meter, but I have to use maybe 50 meter or 60 meter, but not 100, because at 100 I am over the capability of decoding the signal. This is the reason why we are using the coax cable only for very short distance. This problem does not exist in optical fiber, because the optical fiber inherently they have the capability to transport high data rate on very long distance. So let's see the next one. Any question?
It's okay.
Hello? No. This table gives us the comparison between resolution and dimension of the screen. Well, the first one is old analog TV 4x3, and we don't care about because was a different standard. But starting from HDTV, which is aspect ratio 1.77, which means 16 by 9, if we move from HDTV to 4K, you can see that this area is 4 times that one. There is in 4K another standard, which is this one, 4096 for 2000 lines, which is used in cinema and is called DCI, which means Digital Cinema Initiative. And the aspect ratio is not 1.77, but is 1.89. It's more anamorphic, which in cinema is very used. If we compare this one, this area, to the last one, which is 8K, you can see that this area is 4 times that one. So every time we double the horizontal resolution, the total area increased by 4. Then it doesn't mean increase by 4, but also increase the data rate. More pixel means more data, always. And one of the big limitation that we have today about the number of the pixel that we can, there are two main limitation. One is represented by the screen, because the elementary pixel, the dimension of the elementary pixel that you can get, you can build into a screen is not infinitesimal. It has a dimension. Then if you put more pixel in the screen, you have the requirement to have a big screen. Otherwise, you cannot fit all the pixel there. And the second problem is the processing data rate, because if you use high resolution system and you have a lot of pixel, and each pixel is coded by 10 bits, that means you have the necessity to have a very high big power processing for the picture. Otherwise you lose something, you lose frame or you lose other information. There has many years ago, I mean more than 10 years ago, one of the problems that comes up was the everywhere in the world comes up different standard about high resolution. In Europe there were one, in South America another one, in North America another. In Japan they use NHK standard. This was a very dangerous situation, because you cannot exchange a program between maybe Japan to South America or between South America to Europe, simply because you need to be you need your material be converted many times, and that means you lose quality. More or less 15 years ago, SMPTE says, okay, we have to do something. And with the ETU, International Telecommunication Unit, they define a standard, which is common, it's called CIF, which is Common Image Format. So what does it mean? It means that we are talking about the visible pixel always. If in Japan we talk about HD. HD is 1920 pixel per line. And if we are in North America and we speak about HD, still 1920 pixel per line. Doesn't matter if the non-visible pixels are different. The important thing is the visible pixels are exactly the same everywhere in the world. This is called common image format. And as you can see, the common image format is independent from the picture rate. Maybe in North America, Canada, and Japan, uh, they use often 60 frames per second, 30 progressive segmented, and 60 interlaced. In Europe, uh, in many African countries like Algeria, and in some other countries like South America, they use 50 frames per second or 25 frames per second. In cinema, they use 24 frames per second. But independently from the picture rate, the common image format have as always the same pixel number per line and number of line. Any question? Hello? No. Okay. Now, this is a more complicated thing. Yeah, let's get back one step. Uh, Marco, please, can you exchange on the whiteboard? Okay. Okay. We know that. Oh, sorry. No. Yeah. Let's see. No. Let's do it this way. It's better. Okay. This is a video cable. Okay. We have already seen from the slide that the basic structure is uh, is 1.5 gigabit per second. But in this case, we are talking about HD at 50 fields per second, or 25 frame per second. um, let's talk about 25 frames per second. We are working at 12G at 50 frame per second. So 12G is a standard composed by four channel of video. Each one is 3G. At the very beginning of the 4K standard, 12G was not developed, and all the device which was working in 4K, they had 4 cable in and 4 cable output, because the bandwidth required is very high, and the technology at that time was only available for maximum 3G on a cable. Later on, technology has evolved, and then they put 3G on a single cable, 12G. But 12G is just a way to transport 3-channel 3G in one cable. The real standard is always 3G. That means, if I go here, Marco, please, can you switch to slide? Okay. Here we have a picture 4K, but this picture is composed by 4 pictures different. Each one is 3G. Of course, if we use 4 cable to move this picture from one side to another, and one cable for some reason will be broken, or the amplifier in the middle is fault or whatever, what we receive is 3 picture, but the other one is black. Of course, this kind of a situation is not acceptable. Or it is acceptable for a very particular situation. The next step has been to develop a way to overcome this limitation. And the way to overcome that one is called 2SI, which means two sample interleave. So what does it mean? It means my picture is 4K. I bring 2 pixels from subimage 1. The adjacent pixel 2 are from subimage 2, and so on. The next line, I have 2 pixels, the first from subimage 3, and the other 2 from subimage 4. In other words, I have merged 4 subimage in one big image. If I lose one subimage, I lose maybe those 2 pixels, those two, but the rest of the pixels still there. So decrease the resolution of the picture, but the picture still visible. And this technique is called 2SI, or two sample interleave. In GMA, we use two sample interleave techniques. Any question? Okay.
Proceed.
What? Sorry?
Proceed.
Okay. So this is, I mean, the last part of the technical for the video together: magic number, resolution dimension, and 2SI. Few words about digital audio, because in GMA we have different kind of audio transport, and one of that type is the AS audio. AS audio or digital audio is composed by uh, two subframe, and each subframe is composed by 32-bit. Two subframe are on the same cable, but one subframe is one channel and the other subframe is another channel. That means on one cable we have two audio channels. The sampling rate in GMA is 48 kilohertz, and of course the data rate on each audio cable is the sample rate multiplied by the number of the bit multiplied by 2, which means around 3 megabits per second on an audio cable. Not all the audio cable can transport this data rate because, you know, audio normally is from 20 to 20 kilohertz. It's so far away from megabit. 3.72 megabit means 1.5 megahertz. But we are lucky because if we use cable for digital audio, this cable is also perfect for analog audio. That means in GMA we have analog audio and digital audio, but we can use the same type of cable because it's always perfect for both. In that case, we have all the audio cable are for digital audio, which is perfect for analog also. This is the last slides, and it is very interesting because it gives us some information. The information are, if you look where is my cursor now, we have at the input of the instruments a signal which is 4K because it's 3000 pixel, 2000 line, 50 frame per second. It's coded, as I told you, in luminance and the two channel color difference is called R minus B is called the CB, and R minus B Y is called the CR. A 10-bit, it's a 12G type, but it tells us that this signal is composed by 4 sub video. Each one is HD at 50 frame per second, means 3G. So this single signal on this wire is composed by 4 sub signal. Each one is 3G. And we have audio embedded from channel 1 to 16 only on sub 1. In theory and in practice, we may have 16 channel audio for each sub video. A total of 16, 16, 16, and 16 means 64 audio channel. So the 12G can transport 64 audio channel embedded. So we have 64 channel on 12G mode, or we have space for 64 audio channel on 12G mode. But for our choice has been to use just 16 audio channel in total, concentrated on sub 1. That means the sub video 1, which is an HD 3G signal, will contains all the 16 audio channel. This is to have a compatibility with the HD side of the GMA, because when we convert from 12G to the HD mode, we can feed the entire audio system 16 channel in one HD channel, which is our output. That means we have at audio level a compatibility with between 12G and HD mode. Of course, the drawback of this technology is if we lose the video sub 1, all the other channels are lost. And because all the other channels are concentrated on the sub 1. For this reason, in the TOC, Technical Operations Center, where we can connect the external device like OBVAN, for redundancy, we have some other audio path like analog audio, AS audio, and Dante network. In case of troubles on the embedded audio, the same audio can be cached on analog, AS, or Dante, which are always available. So this is the last slide for today, and we will meet again tomorrow. Thank you.